Thank you, everybody, for coming. I know there's some really good talks in the other rooms. You can tell because there's a lot of people at those. You'll have to go or compare notes with someone else. Some of you know me, some of you don't. I have a job. It's called IBM Java. But I also do JavaScript, so if you hate Java and love JavaScript, I'm your man. And I do other things too, including other runtimes, which I'll maybe talk about if I get to it. I've been doing virtual machines for a long time. I'm J9 and things like Eclipse. But I have to confess up front, I'm moving to Java talk, but small talk is still the love of my life. So there you go. I didn't submit an abstract. I kept being harassed 87 times by George and Hangita. And so last night I wrote one, as you can imagine. Actually, I wrote this on Mother's Day, to be honest. My mom asked me, what are you doing in Chicago? And I said, I'm talking about you. She was all freaked out. I said, you are a virtual machine. You protect me from unsafe pointers and clean up after me like the garbage collector does. And here's where I am. Sorry, Mom, I'm a VM guy. However, moms don't know best always. We grow up, so there's some things I'd like to talk about that are not quite mom approved. All right? So today we're going to talk about a virtual machine. I'm going to talk about the one I'm familiar with, so J9. That sort of sets the baseline of what I would say current generation VMs. And then I was going to talk about what's happening in some of the hardware things and some of the stuff we've done to address those issues and where Java could go. And then we can discuss the bar. So if you don't know, who knows what J9 is? Who loves J9? Come on. There's a lover of J9. Right to the front, you win a prize. The rest of you, out. It's a design from scratch by IBM, high performance, high reliability. Everyone says those things. We mean it. So that's good. It scales. It started as an embedded VM, and it's super highly configurable. We've got a VM called J9. You know, everything that modern VMs have, it's got plus more. So, and I was going to talk about some of those things and show you some pictures and things like that. This is known as the VM is a VM is a VM chart. Okay? What people don't know is that J9 will run all of those libraries. The same VM will run, for example, SE6, SE7, SE5, if you like. Plug and play. We don't support all those configurations. It's going to be madness. But a VM, literally as a VM is a VM. We'll run MID-P, we'll run CDC and embedded. It's very configurable. We can shrink it to a few hundred K, and we can also ship it in its full figured form. And all of those are typically trade-offs, either speed, space, or some particular functionality that's not needed for embedded and things like that. And you're pretty vanilla, I would say. I call it a vanilla design because a lot of designs look like this. They have pluggable components like JITs. They have pluggable GCs. We have many. I'll tell you about a few of them. We have pluggable tools. So a lot of this stuff is composable. So J9 is one of these VMs that shrinks or grows depending on the need of what you need to run. Okay? It's got a bunch of portability stuff so that we can run on. We've done pretty much every processor and platform known to man. We don't support them all because we don't have products on all of those. It's just expensive, but it's a very portable, very fast virtual machine, and that's par for the course these days. It has this, wow, hard to see, very funny colored set of things. But we have a compiler called Testarossa, named after the guy with the red hair who works on it. And it's, I would say, one of the more aggressive optimizing Java compilers on the planet. It has a lot of what we call intermediate representation generators. It has a ton of optimizations. And depending on how big you'd like your JIT to be and how much performance you'd like, you can mix and match and or, from our perspective, take out optimizations or add more. So you can actually dial in the correct target. So we have smaller versions of Testarossa that are targeted at 500K systems versus the full end for the high server. And the only difference is some of the optimizations you choose to include in the build, which are turned on or off by flags, you just don't include them. So you may not do some of the expensive ones because you can't afford it on an embedded system, but you certainly want to do that on a server. So you can maybe read that, hopefully, but it's a fairly aggressive just-in-time compiler, and it has these 5 phases in addition to interpretation. So everyone does this, right? Everyone in the Java world does this. well, maybe not 5 levels of optimization, but so we have quite an aggressive set of optimizations. You start with an interpreter, it does profiling, it tells you what's hot. You may go to cold, which is just fairly basic. You can skip to warm, which is a higher level of optimization. And then from warm, you can go hot, profile, or scorching. And so the more you run, the more information we have about what you're running and what we should optimize. And when you run it enough times, we'll flip you into what we would call very aggressive compilations. You can actually see that over time watching an app. It'll take this time, and then you'll see some optimizations kick in. It'll go down and go down. And then, of course, we can decompile and recompile when we make mistakes. Okay, so that's a pretty much, I would say, yet again, standard for Java, less so for other languages that aren't quite as mature in terms of their implementations. Profiling is interesting because today's technology, it's a thread that sort of sits on the sides, rummages through your stacks for a while, sees what's important, and then feeds the JIT and says, you're doing it wrong. Flip that into a better optimization than you were doing last time, okay? And it's very, very low overhead. And then scorching, of course, is the the highest, fastest. So what does that actually mean? I found an old chart, so I put it up here. No one ever publishes or shows this kind of stuff, but here's some pretty not Java code. It's kind of C code, but Java syntax, I guess, loops and some math and stuff like that. But if you look at the progression through the cold through scorching, you'll see cold, smallest amount of code. You could tweet that amount of code, actually. It fits within the 140 characters, so that's pretty cool. Doesn't take very long to compile, but 2 milliseconds is a lot of time. But you'll see that the wall time is, so that'll be like 6 or 7% of your overall time will be compilation time at cold, and significantly more percent of your time for compilation time at scorching. So you don't want to spend a lot of time doing scorching, but you want to find the right stuff. And as you can see, you can go about 5 or 6x based on this particular example, which is remarkably not object-oriented. So but it's a simple example you can see. This code will have about 35 or 36 bytecodes generated, this whole class, and one of them is a GOTO statement. So for those of you at the GOTO conference, GOTO considered useful in code that Java compiles frequently. So I have a GOTO considered harmful somewhere, but it's not, it's used all the time. We have a whack of GCs. GCs are good, more GCs are better. So we have, of course, everyone does this now, fully type accurate, parallel, partial concurrency at a global level. If Gil was here, is he here? He's somewhere else, doesn't matter. So I told Gil I'd mention his name twice. There is a stop the world phase here. I have to say that out loud or Gil will say nasty things at the back or something. But there's fairly aggressive parallelism in all modes on, actually I'll tell you a few about some of these modes. And we have a common code base across all our ME and SE platforms, so it's pretty nice to be able to get some of these GCs in platforms you may not normally get, so in embedded systems. I'm not going to talk about every single one of these, but if you have a particular workload, we will have the GC for you. That's good news. So the state of the art says there's a lot of very high implementation, high quality, high performance implementations in garbage collection. The bad news, which, VM implementers have to be a little bit honest here, is that there's choices which make it more complex in some cases to choose. How are you going to choose? So you do have to know how to choose, and we have ways to guide you to that. So we have the basically stop the world, get it done really quickly in parallel. We have the concurrent version that says we're going to do a little collection over time. Those are the top two. We have a generational collector, which is the best of a generational scavenger. Picks up all your garbage quickly. If you make a lot, that's actually a really good thing. And then if your garbage or your objects live long enough, they end up in tenure space, and that's done concurrently. And then we have this temporarily insanity called large heap multi-core, which has been replaced by a new larger heap GC. So subpool is dead, and balanced is our new technology, which I am going to talk a little bit about. So there's lots of GCs. I tell you some technical details. Who wants to know about garbage collection? Who's a garbage collection expert? You an expert? I saw. My hand goes down too slowly. So we have a GC called balanced. The trend in GCs is to have region-based GCs, so you can do partial collection and look at regions differently. So we've designed this for our next generation VMs. This is now in our current one, so it's hard to say our current VM is the next gen, but it's the foundation for some interesting future optimizations. So the first thing we can do is gather objects with common properties. So that's things like sibling. That's two objects that don't actually point to each other, but are pointed to by someone else, but are accessed together, okay? So they'd be side by side. Parent-child, so that's two objects that might get accessed by some pointer chasing. You might put them in the same region for some reason. Lifetime, birthplace, and resting place. You might want to know where or how or when an object gets born, where it's going to die, and probably how long it's going to live, and those kinds of things. And then there's this level of read-onlyness, right? Is it no level of read-onlyness, as in it's pounded to heck by read writers? Is it partially read-only, like 90% of your objects are only read from most of the time and were written to once or twice or maybe 5 times at most, and that's it? So mostly read-only, or is it really read-only? And is it hardware-enforced read-onlyness? So stuff like that. So the reason you want to do that, placement, improve your cache performance. If you put two objects side by side, they're on the same cache line. I touch them both. I touch one, the other one's available quickly. Allocation efficiency. You wouldn't believe how annoying it is to have an object that lives long enough to be tenured when you should have put it in the tenure space initially. So if you know an object's going to live a long time, you'd want to do the right things. And so this allows us to decide where objects are. And the interesting part about balance is we can actually move them if we got it wrong very, very quickly, because we keep an inter-object reference across all regions. Pretty fancy schmancy. And the other thing is the reduced working set. We can actually figure out that your objects aren't being used and put them in a page they'll get swapped. And we can also figure out that they're being used a lot and put them in hot pages and segregate those for better paging. So for things like cloud, it's another useful thing. The other thing that this allows us to do is manage, or I'm going to talk too long on this one. I have to talk faster. Is manage memory based on memory characteristics. So the memory could be fast or slow. The memory could be memory mapped, could be read-only, could be a lot of different things. So the memory itself will have different characteristics than the objects that you put in them. And so our job there is to place objects where the memory is, the memory characteristics are best applicable to the way you're going to use the object. So an example would be if you're going to, well, NUMA is a fine example because you'd like to access the memory from the fastest location from the processor that's accessing it. So you need to know what NUMA regions attach to which processors. And then if you do things like that, you can get 5, 6x, x as in a multiplier, scalability on things like a power system. Because being close to your memory is super important. Okay? And so we can also in J9 optimize based on memory characteristics and things like tiered memory. So you can have SSD mapped into direct memory access now. So you can actually put objects in there if you wanted to, but you better make them mostly read-only because they're flash-based and it's going to cost you a lot to write to them, maybe not so much to read. Okay, so things like that, and like multi-core scale. And of course, the region-based GC is the very first use, which is in production now, is very large heap GC. So we are productive every time we decide to pick on a region and empty it. So results-based GC is kind of nice to have. And we have a soft real-time version as well that'll actually allow you to do soft real-time stuff. So this is something that I want to talk about a little bit because later you'll see some of the things we're doing and how it's leveraging sort of, hopefully the words you'll remember what I said earlier. Okay? We also do crazy things like share code across address spaces, kind of like a DLL, but since Java's dynamic, you have to make that on the fly. So dynamic class sharing, it's called the shared classes cache. We do two things that are interesting. One, we put your class code in there, so you can save 50, 100 megabytes per instance. If you run a lot of them in the cloud, you're going to save memory. The other thing we put in there is code. So the previous guy compiled all your code to start up. We put it on disk. Next time the next guy starts up, reuses that code, saves 20 to 30% startup time, mainly because you're not recompiling object again and again and again. Okay? We call this compile once, run manywhere, which is a play on the Run once, write once, run anywhere, I guess. Test everywhere. How does this translate? I don't have a lot of these, so don't worry, you're not going to see. But every software release has been driving 20, 30, 40% improvement. And this chart was chosen because it shows you the progression of hardware, which is the lighter boxes, and then the software. So they're directly comparable. You'll see a 57% jump in hardware performance, another 40 by software, identical on identical hardware. So we have for folks who work in the Java world, you cannot believe how crappy the old VMs were until you see these charts. You say, oh yeah, it's 6 times faster than it used to be combined hardware software. And a lot of that, probably over half, is the software-only improvements. And this is true not just on System Z, it's been proven true on both x86 and Power. Continual investment in Java has done a really great job. So the state of the art is the best VMs on the planet are currently Java VMs, and ours is one of them, and there's a few others that we could probably mention, but I can't remember their names, so I won't. Right, George? All right. Tools. We, in the Java world, have an embarrassment of riches of tools. The VM knows more about your application than you've ever seen in your entire life, more stuff you don't even want to know. And so we have a suite of tools. Lots of people have tools like this, but Java's embarrassment of riches here. Really great tools. I think Charles is going to talk about tools for GC, I guess. We provide a bunch in Health Center, and they're kind of nice. What we do that's kind of unique is, remember all those GC modes? How do you pick? You run the tool, it'll tell you. So for example, in this case, there's tuning recommendations. One, your app's doing something abusive, like calling system GC. 2, your app's got too much memory because we noticed your working set is tiny. 3, maybe some other hints that you picked the wrong mode. So if you run the tool, it'll actually tell you what GC mode might be best for you. Now that's convenient if you're having trouble tuning. Maybe less convenient than if we figured it automatically and switched on the fly, but that's not quite within reach of most GC algorithms to switch on the fly like that. So we'll have to work on that. Some of those tools are download and run locally, but guess what? You're not going to be doing that anymore. So IBM, and you can go to the Wait site, waitibm.com, has cloud-based monitoring. So you can actually say, take this VM, kick it, send all the results to Wait, and Wait will provide these beautiful charts. So you can go to the Wait site now live and see how it could help you. But what it does is it does really nice analysis, and it'll show you what's interesting in your application and where you're spending excessive amounts of time. So if you have a chance, check that out. So VMs are perfect, right? Right? All right, we're done. I can just go. I was hoping. Not really. We got a shellac load of stuff to do. Cloud. How many times have you heard of cloud? I put it in quotes because it's not really well defined. But from my perspective, it's the use of things like virtualization, heavy virtualization, which involves a couple things. One, the hardware is being abstracted to the point that we call it the layer of liars. The hardware is real, but there's a hypervisor in the way that says, no, you've got 2 cores, sucker, and no, there's 8. Or it tells you have 8 and there's only 2. So you're being lied to, and then the OS takes that lie and compounds it by lying some more and telling you have all the memory on the planet, and yeah, of course you have 8 cores, but reality is you've been sliced to only 1/10 of a core, and all of your algorithms assume you have them all. So the layer of liars is a real problem in systems that are abusively virtualized, which is happening more and more. And that's pushing on footprint and density and things like add and delete virtual CPUs. So if someone says, oh, I used to have 2 cores and now there's 4 cores, most VMs, except ours, I think, will add and adapt to that on the fly. They'll add more GC threads, or remove GC threads, they'll add or delete memory on the fly, and adapt to whatever you've done to the VM. Okay, so that's, I would say, the leading edge and the new normal for VMs. Okay? Big, everyone's attacking this problem. I call it big star.star. That's more data, more threads. We can talk about that in a second. The other one I want to talk about is compatibility. It's the least sexy thing I could talk about today. So I'm gonna, just to prove a point. And you'll see what I mean. And then there's some hardware stuff I wanted to mention, and of course I can't ignore security. I'm not sure I'll do all of these, but we'll see which ones come up. And so the questions for a VM guy is, we've solved all these things. We've invented some of the best optimization and runtime technology possible. Okay? So we have this really great stuff. What do we do to solve the stuff we haven't solved yet? And these are some of the problems I see. If you see more problems, I'd be happy to talk to you afterwards, but I got a pretty good list. I'm sure that overlaps with yours. So this ends up, I call it the wish list. We got to solve all these things and then add a bunch of other stuff like resource control and capabilities and language extensions and high performance memory model and generics and I said true lambdas. Sorry. And 200 other things. So I'm not going to talk about almost any of these, although I will touch on them in the following section. So the first one's cloud. So the thing that's happening in our world for cloud is you're seeing these deployments where the machine isn't yours. And they're getting overcommitted, they're getting reconfigured. The pressure on these things, not in all cases, some cases you buy the box, you get exactly what they're claiming. But in some clouds, you're actually getting less. And over time, you're going to see these things become expensive. So the first thing you want to do is fix or improve Java density. So the ability to stack or run lots and lots of JVMs, okay, on a single box, the more the merrier, to fully use the resource that you're paying for. And then the ability to potentially stack. Okay, so this chart's here not because it's actually not even that pretty. It's here because we have a dial that goes to 11. Right? And that's the feature for you. But the spectrum goes from infrastructure as a service like an Amazon. How many VMs can you run on the hardware you've rented? Okay? And the technology we put in there are things like the shared classes I mentioned earlier. I can run a lot more VMs because I share, which is reducing your individual amortized cost per VM. They come up faster, they go down faster, so you can have a much more dynamic system. But you're still in the megabytes or double-digit megabyte footprint. So it's fairly big. You can improve that a couple, 1x, 2x by stripping and reducing profiles in Java 8 and stuff like that. You can get a little bigger, but that's not a huge savings. And that's, maybe you don't care unless you start paying by the hour. Who pays for cloud by the hour? Well, everyone will. And so you're going to care that you can either use more in the hour price that if you're buying a gigabyte's worth, wouldn't you like to put twice as much load on it than if you didn't have to pay? There's middle of the ground, which is a 10x to 20x improvement. That's things like isolates, which is a Java standard. And that would be a form of multi-tenancy with process isolation. And then we have some other stuff that we call snapshots, which is being not really used by that many folks, although there are VMs on certain cell phones, for example, that use this exact sharing model. And then there's PaaS models, which is heavy multi-tenant, super small instance models, and that's 50 or 10K per process. So what I'm going to talk about a little bit is multi-tenancy. So one of the things we have, and this is in our Java 7.1, you can just go download it at the IBM website and try it out. But basically what we do is we allow you to virtualize within a JVM and run multiple JVMs within a JVM. Duh, right? No brainer. And what you share there are lots of the underlying class library implementation. The JIT code is completely shared across all the instances, but we isolate. So we isolate statics. So if you have a single class and it's loaded and you've got it in 2 tenants, you've got 2 copies of the statics, 2 different things. So within a VM, that's a separate VM, okay? And then of course you save a shellac load of memory and some other things, okay? The other thing we do is not just keep you apart memory-wise in terms of statics. So the fact is you have a static variable that I don't want yours and mine to conflict. We also have a model which isolates resources. So I would say this is in the bleeding edge of what VMs can do today, and I think it's still early days. The ability to host pieces or other applications within your Java VM. An example would be untrusted you sends me an app. I'm not going to pick on you, but you send me a component, and I don't really trust it. Why can't I run it in an isolated context? Why can't I say, you're not allowed to create threads in your library. You're not allowed to do certain things in your library. It's not a security thing. I just don't want you allocating 600 gigabytes and or forking 32 million threads. Why can't I control stuff within my own VM differently than for component reuse and things like that, right? So that's a use case. But you could also write an app server that does that. It takes a bunch of apps, loads them, and completely controls how they're allowed to be run, okay? So in how does this look? We did an extension that allows you to do this to Java code. I'm not sure how it would look in a standard Java when brought to a standards effort, but initially you just annotate and you could say these are tenants or not, tenant scope or not. So in this case, the default locale for two different apps, one's the UK, one's USA, and Canada is the default. You get two different apps and they get two different locales in the same address space. Fancy, eh? And for multi-tenant loader, which I'll show you in a second, we just make that tenant scope the default for all statics. But if you're doing fancy class loader tricks and doing app servers, you would love to have the app server be a lot smarter and share components that are shareable, things that are read-only, for example, which would be really nice. Oops. An example here on play well with others, the kindergarten model within the JVM. If I bring two apps in the same JVM, I might need them to prevent them from fighting with each other and not starving each other, right? So we have the ability to do that kind of stuff. If I was able to not change my screen resolution, you know, multi-tenant CVMs also have, can I actually see? Oh, I better do this and run whatever I think I'm going to run. Anything look like the word demo here? Oh, there we go. So for example, the multi-tenant VM also has other benefits. If you run it, you'll see the command line here on my left, your left too, I guess. Standard VM runs like that. Multi-tenant VM actually has other benefits like extremely fast startup. Why? Because the VMs are already there. So you're really just stacking onto something that's already running. But you can run, I don't know what the number's going to be by here, but let's find out. Yeah, 3 to 4x faster on startup. So for certain kinds of apps, you might find a run and done model finally feasible stacked on top of a multi-tenant VM. Right? Okay. So big, what's that mean? More threads, more memory, more problems. That's sort of good. I just want to talk about some cool stuff like hardware transactional memory. Who knows what that is? Who wants this so badly? Well, you'll have to wait on Intel, but you can get it on Power and on Z. But you can wait a few months, I guess, on Intel and see what happens. So basically, this is called concurrency, get lucky concurrency. It's true. You don't lock. You just say what's important to you. Between here and here, don't keep out of my pool. And what will happen is the hardware will detect if anyone else has messed with your memory while you're looking at it or touching it or reading it or fondling it or whatever you do to it, it will detect. And it will tell you. And at the end, you'll go, oh, crap. But you didn't have to lock. You just said, please inform me if anyone messes with my stuff. And at the end, it tells you someone messed with it or it succeeded. And so you get this all or nothing. The interesting part about this is you can do all sorts of great stuff, like get rid of actual locks, because most of the time the lock is way, way, way overkill. Lock, do some trivial thing, unlock. So things like Java util concurrently queue. On our systems with transactional memory, you'll get 2x scalability, right? Why is that? Because you don't end up locking. You end up just telling the hardware to detect if you had a conflict, and if so, back out, right? Same for readers. Lock elision, the removal of locks, which is what the word elision means, is basically if anyone modifies the thing I'm reading under this transaction, back out and do it the hard way. So you'll start to see all those, some of these scalability problems. You'll see what happened to my app. I used to overlock. If you have a badly written app, which someone else gave me code, and it's going to scale a lot better. So you're going to see a lot better scalability in JVM. So I wanted to point that out. But the really interesting thing is this can be used for something called GIL removal. I'm not referring to Gil, who's not here. I'm referring to the global interpreter locks in crappy interpreters like Ruby and other things like that, okay? Where you have a serialized interpreter loop. Well, guess IBM Research, you can look this up, did a hardware transaction memory thing where they get lucky concurrency used around the bytecode implementations of Ruby, and they got 4.3 4x scalability using what I would call get lucky concurrency. Get lucky as in remove all locks, protect with hardware detection for the locks you didn't need in the first place, and if you get a lock, if you get a problem, go fix it at that point. But most of the time, the fact that they lock the interpreter to run it is excessive. So, all right. I'm going to skip that one because I wanted to get to this one. So this is the one I said was what, boring? No? You're going to tell me I have no time, right? It wasn't sexy, yes. Well, this is something that bothers me because our customers rely on us to give them compatibility. And we love compatibility. And so what we decided to do is protect them by never breaking their code, but also prevents us from innovating. I have code from, I don't know where it comes from, but it's compiled with 1.0 and it has to run and they don't have the source anymore. So we've reached COBOL level. I don't have the source anymore. It's true. So ridiculously old code. The word was used ludicrously this morning. Ludicrous, some scaling. There's ludicrous and ridiculous now are the two words that I like today. And eternal binding compatibility is different. So I want to drive some sort of path into JVMs that helps you with both compatibility and migration. So this hasn't happened ever before until Java 8. Do you know this? Does anyone know this? Compatibility was don't change your code, just be very careful and hope it doesn't break. All right, there you go. Now, kudos to the extension, the biggest innovation in Java 8. You hear lambdas, woo, but that's just because it's sexy. This is the innovation, okay? Wow, there's some font funniness here. But what happened was, if you want to extend an interface today, and you add a new method to it, guess what happens? Everybody who implements it breaks, slap to the face. So then what happens? You're not allowed to do that. You create a whole new one, interface 1 and interface 2. And somewhere in your code, you will cast to determine which one that is. That's a complete idiotic disaster if you have shellac loads of code. So this was the light. Compatibility, bing, finally. So what you can do is you can say, not only am I going to make you implement this new method, but if you don't have it, here's a free one. So in the end, what you're doing to people is maybe you would have broken them, but you're giving them a workaround or a fix to that breakage. So they will be eternally grateful, hopefully. But it means that there's a path to fix Java over time. This is one of them, where you can actually change APIs and potentially evolve the libraries, evolve things in a compatible way that's predictable, protect the investment, move folks off of potentially the wrong or dangerous things, but still run all the code that they know and love. Okay, so this one here is nice. So I wanted to make sure that you understood the importance of it, because sexy is Lambda, but default methods are valuable. Okay, so I wanted to talk just quickly about. Can I have some more, please? So what I wanted to talk about was API evolution supported by the JVM. How much time do I have? 15, oh, lots of time, okay, good. So why doesn't the JVM give you trusted mechanisms to do field renames or method renames? I know you missed the two Gil jokes, but sorry, I'll throw Gil's here, so it's good. Method rename, for example, clearly you've named your methods properly the first time you wrote the code, right? No, of course you want to rename stuff all the time, but you're not going to for compatibility reasons. Or you add a method if it's a class or something, right? So what you want to do is be able to have a specified way to evolve your class libraries along to sort of kind of support the kind of things that people want to do to make their code better, refactoring. Right now, refactoring is done by lots of people, but they break everything when they do it. How often have you refactored yourself into broken code? Tons of times, right? You just don't have a whole worldview to do that, so that's a problem. So I want, for example, selected visibility of methods based on compile time versions. We do this now. CDC on a JVM can only see the CDC methods, and a CLDC on a standard JVM, which has more implementation underneath, can only see the CLDC methods. So in embedded, we actually can run, CLDC mid-P and on a CDC VM, but be compliant, because you only see the methods you're allowed to see, which is the platform view versus the implementation view, right? So those kinds of things can help you. And then I'd like, for example, when I break your code and you hate me, you know what I'd like? If you got the jar and Eclipse or IntelliJ or whatever your favorite IDE is, refactors for you. Says, by the way, old method, new method, I did this fine refactoring, so you didn't have to do anything, and you were transported to the fine future of the better APIs. Serialization robustness, this is based on, we should do something about versioning in classes, for example. And if you did that, death to the bogus serial version UID, which is just this thing that's a hack to survive bad serialization. And then you can do things, the bottom one is the one I want to do, things like thread stop. The VMs have lots of crazy stuff to make that work and be safe. It's deprecated, you shouldn't use it. I want a way to actually enforce deprecated disappeared as opposed to deprecated is just more warnings. Like so, you shouldn't use it, but everyone continues to. So example that you can see, I've talked about this one before, is if you had versions, and if you were able to specify something like the deprecated in V1 or something, or deprecated in V1 to V2, I made the syntax up, I don't want to argue about syntax, what could you do with that? Well, you could get rid of bad field, and you could, between version 1s and 2s and version 3s, if you had versioning at the class level, or maybe bolted on metadata. There's lots of ways to consider this, but if the Java VM could then say, you know what, if a version 1.0 shows up, I have a bad field for you. Or I'm going to rewrite that with some getters and setters. If version 2 shows up, you should have known better, but you're still allowed to use it at that point. But I rewrote you as well. And if version 3 showed up, the fact that I compiled against the version 3 with the version 3 meant you couldn't have compiled that successfully in the first place, so the method doesn't have to be there. So in some way you have a way to get, who wants to bury some bad behavior in Java code by removing one person, right? Imagine this feature, right? So that's number one. I also wanted to get to some more charts. I told you I had like, a lot of charts. Oh. Here's one near and dear to my heart, hardware. Who knows what a GPU is? Who wants to abuse GPUs in their application? Yeah. How many of you know that Java is in the way between you and your beloved GPUs? Giggling. Java is in the way. I gotta transfer the data. It's not in the right format. I have to mess with it till it works kind of thing. It's awful. So we wanted to do something that helps with that particular problem and a few others. So the fact is, you know, Java protects you. My mom told me exactly how to lay out my memory for me. She didn't know about GPUs. So I want to fix that. And I want to fix a few other things. Serialization and I/O. I want to be able to do direct native access because guess what? Some of that memory is externally on GPUs or some of it's just in a database in database format. Why do I need to convert it into Java heap format to munge through it? So Java does a really great job of protecting you from that. Doesn't do a really great job of giving you access to that while giving you safe access. So we did this thing called packed objects. We've been working with folks in Oracle and others in the community about how to bring packed objects into, or the functionality that packed objects provides into the Java platform. And the kind of use cases are things like no copying to and from the database for persistent data. No munging on the wire protocol if it's coming through RDMA, direct memory mapped I/O. And the third one would be no serialization, deserialization, which is kind of like the no copying on the database side. Okay. The other thing that we want to do is make it a lot easier to have more compact data. So packed, one of the things that Java does kind of poorly is it's just got memory bloat. You've got headers on objects, everything's a pointer to some other object. So things like, say, an array of things, there's overhead, a lot of overhead at times, and the layout is not predictable. It could be scattered all over the heap and all sorts of places. So things like packed objects give you an opportunity to take objects and, for example, in this particular case, a packed line is actually 3 points minus their headers packed into one object. Now what does that get you? Cache efficiency, great performance, and size. And if you're going to send this off to a GPU, it's pretty much a mem copy. So a lot nicer, that kind of thing. And so we did a prototype, and I don't expect you to learn it all here. You can download it and try it. It's also on the IBM website if you like, and give us feedback, because one of the things we're trying to do is figure out how customers are really going to use this, and whether or not the things that we're seeing as to benefit us as VM implementers will also benefit folks who are really down by the metal doing GPU stuff and things like that. This is another example of a reason packed objects exist, direct memory access, otherwise you're reifying it or copying into the Java heap just to talk to it, okay? And this is an example of us actually, the syntax. So the syntax, I actually don't like to argue about syntax because it's the most trivial part, but essentially the definition of a class, put some annotations on it, and I can either get an on-heap one, which is part of the garbage collected heap, or if I need to, I can take that exact same class and point it externally. And if you look at things like byte field setting, double field, and Boolean field, the code is identical. So you could actually have the same Java code talking to something you got from the off disk, or something you decided to have in memory, and no mental model really has to change for how you're going to program against that. And the layout is designed by you, so more safe for more you. Okay, who liked all of that stuff and wants more? Bar. So I want to talk about one more thing and then questions. So I really am going to finish 50 charts in an hour. So my job has grown to not just be Java. I have a JavaScript runtime that I own and ship on IBM Cloud. And in my history, we've also done, well, small talk, PHP. We're seeing Ruby, Python, PHP frequently in our customer sites. How many use any of those languages? Right? In anger or just for fun, or are you angry? PaaS is like Cloud Foundry, used by Heroku, IBM Bluemix, many, is a polyglot platform. So you're seeing a lot of these languages for doing things like consuming services that are available, data services, things like that. So what we're seeing in IBM is our customers aren't just becoming Java programmers. They're becoming Java plus programmers. Java plus JavaScript, which you saw earlier with Trisha's Livewire, Highwire Act. And I'm not going to code for you today. But I will show you some code in a second, maybe. And then JavaScript is this hugely popular language that's coming along. So as part of this new job that I've been doing, I've noticed that all virtual machines except the Java ones kind of suck in terms of we call it modern implementation. They're 10, 20 years behind. They're perfectly good 1980s VMs. They're not so modern, right? They don't do parallel things. They don't have high-end code, JIT compilation. They don't take advantage of modern hardware features. Well, they're nice to play and they do okay, but we know that some of the techniques we've done in Java should be applied to those. So my question that I ask is, why has the universe not adopted the JVM as the one true runtime? Right? The answer is because the Java bytecode set isn't the best place to do multi-language development. It's not. So the question is, how do you get there, and how do you leverage it from the investments we made in Java? So that's the question we've been asking. And when we look at our technology, we see garbage collection, language neutral. Our JITs are currently used in 5. The same JIT that's used in Java is used in 5 programming languages. And so we're looking at what would it take. And so if I was to say what's the next generation, because the first stuff is the stuff you just saw, the next is, this. Because we've tried some of these things where existing native implementations have been augmented by technology you find in Java VMs. And there's some very interesting things you can do. So parallel GC under some of these is actually quite interesting because they don't have it, and they won't have it, not unless we find a way to enable those things. And it's very hard for you to get that going through the Java bytecode set and keeping all of the fidelity of the language. It's not that easy to get multi-language on Java to work like you want it to if your original language is the language you're porting. It's okay for some things, like JRuby's done a great job, but it's taken them forever to get that performance out of the thing, and it should have been a lot easier than that because of the sheer amount of investment that's gone into Java VMs. So that's my pitch for being invited next year to talk about that. And so here's the 4 things. We're not really done finishing on high performance JITs, GCs. That's going to continue. We are we're starting, but we're not anywhere close to finishing the native layout stuff. That's critical for the evolution of Java. I want language compatibility as another innovation thing, even though it's not sexy, it's what's going to save, the ability of us to continue to push innovation, because we can change things, break something, but give you the gift that fixes it. So you'll take both. You'll say, oh, breaking change. Oh, it fixed it. Happiness. And then, of course, I'd like to speak a few more languages more fluently, and that's an open question which we're looking at. So when I said next generation Java virtual machines, I actually said Java and others. But this is where I am. Questions? I think we're at that time.
Java unsafe, we're pretty dug in on it. Now everybody's demanding that it becomes safe. How much, on the VM side, making them, do you hate us for liking unsafe and using it? Is that motivating some of the packed stuff?
I don't hate you much. The Java unsafe is sort of a necessary evil to get around some of the flaws that are in the lack of the functionality that's there today. So if you have native memory you want to hammer at, that's the really only way to do it without calling out to JNI, which is another long path. So foreign function interface improvements is really critical. So things like unsafe are kind of, I would say, just a necessary evil. I think the right answer for unsafe, in fact, is unspecified. They have to move into some properly specified sort of package of some sort. And if you were to ask what I would do for protecting you from unsafe, is I would be able to sign code that's allowed to use unsafe, and everyone else is not going to be allowed to do it. So just close the scope of who is allowed to be unsafe and try to narrow that aperture, because it really is not, it's not a great thing to do, and it's a really nasty security problem. And then there's virtual machine features like even value types, which could allow unsafe to create unforgeable pointers through the long path, but then once you use them, they're really fast. So they would have some sort of pointer embedded in a value type that then allows you to munge at memory, and range checks is there, and all that's safe or unsafe, I guess, would be the story. So.
Okay, next question. Oh, all the way in the back. Is that a question there? Gil, you going to ask something? No? Okay. Look, you got off easy. Not too many tough questions today. Just one. So thank you, everyone, for joining us for this. Just a reminder that there's a final session in the Java track after the break, which will be Charlie Hunt talking about GC and performance and all that great stuff. And Charlie, as you may know, is the author of the book on Java performance, the one with Duke riding a motorcycle. So you'll definitely want to come and check that out. And thanks, everyone. Thanks, John.